Write the equation of a quantity, whatever that is, that reduces by a factor of 1.5 every 11 seconds. Okay, so is this going to be growth or decay? It's going to be decay, yeah. What do we know about the starting value? Do we know what it is? No. So what you could do is you could let the starting value equal what? 1. It's standard if you don't know what it is to let it equal 1. So we're going to let a sub 0 equal 1, which means 100%. Okay. So we're going to have the amount at time t should be 1 times the base to the t modified power. Okay. So what would the base be if it reduces by 1.5? How'd you get 0.985, Brady? Do we need to subtract this from 1 if we're given the scale factor? If you're given the scale factor, remember the factor is the base. But because it's reducing, not increasing, we have to do something to it. If it's a percentage, Brady, that's when we have to work off of 100. So the question is 1.5 as a decimal is what? Or as a fraction? Is what? 3 over 2. Now, do we want to put 3 over 2 as our base? No, because that would be growth, wouldn't it? So instead of 3 over 2, what do? 2 over 3. There you go. 2 over 3. If it reduces by a factor of 1.5 every 11 seconds, then the base is 2/3. And what would the exponent be if we're measuring t in seconds? Would it be 11 times t or t divided by 11? T divided by 11. Yeah. So if your units are in seconds, and it's customary to just take the units that are given unless you want to change them for some specific reason like we did yesterday, just for the practice of doing it. 11 seconds, 11 is a reasonable number, so we'll just keep our units in seconds. So we could say that right here. T is in seconds. Remember we said yesterday that the units are very important. So we'll just divide by 11. That guarantees now that every multiple of 11, we're getting another 2/3 factor. 2/3, 2/3, 2/3. Yeah. No, it's not. It's not. So if it reduces by a factor of 1.5, that's 3 over 2, right? So what would the base be if it's not the reciprocal? What are you thinking?
Well, I don't know because I was just trying to figure out why you would put 2/3. Because the factor is 1.5, right?
The factor is 1.5. So let's say this. What if I said it reduces by a factor of 2? What if I said it reduces by a factor of 2? Then the base would be 1/2, right? Does that make sense?
So you would put the reciprocal,
So you put the reciprocal of the base there.
even though it doesn't equal that factor.
It does, but we're going in the negative direction. So the reciprocal of 2/3 is 3/2, so it is 1.5 smaller. Yeah. Just like if I said reduces by a factor of 2, it's 1/2. If it reduces by a factor of 3, which would be right in between there, reduced by a factor of 3, then the base would be 1/3. Yeah. It's kind of like when we talk about our dilations, right? If something is decreasing by a factor of 5, it's the a value in front is the reciprocal 1/5. Okay. All right. Good questions this morning. Anything else? All right. Let's get back to where we were over here. If we already did this. We're on part D. So the initial value is 26.3, and it halves every 3 fortnights. Now, I said halves every 3 fortnights, but that's the same as reducing by a factor of what? Well, it's reducing by a factor of 2. Halving is the same as reducing by a factor of 2. If our initial value is 26.3, which is the distance a full marathon is running, I guess the point I'm making in light of our warm-up is what would the base be if we're halving it? It'd be 1/2. What would the base be if we're reducing it by a factor of 2? It would still be 1/2, right? Those two are the same. So one of them is like a vector. You're given the direction, making it smaller by a factor of 2. You have to have the reciprocal there. And It's every 3 fortnights. So if we want to measure t in fortnights, we can just say t divided by 3, where t is in fortnights. That would be a reasonable unit to use, right? Let t equal fortnights, and we just go t divided by 3. But most people don't know what a fortnight is, do we? So what if we wanted to do the exact same thing, but we wanted to go t in weeks? We change it. I like that. We change it. We change it to what? T divided by what?
T divided by 2. Or
Not no. If no, it still happens every 3 fortnights.
T divided by
In other words, 3 fortnights is how many weeks?
6 weeks.
6 weeks. So I could say it halves every 3 fortnights, or I could say it halves every 6 weeks, and that would be the same thing, wouldn't it? That would mean the exact same thing. So if I'm measuring t in weeks, it would be t divided by 6. If I'm measuring t in fortnights, it would be t divided by 3. So your units that you use are very, very important when you define your independent variable units. Okay. Any questions on that? Most of our examples that we've seen then have been growth. We've created some models like this where it gets smaller and smaller, but we haven't seen real life applications of it. So I think we mentioned this in the very beginning when we talked about things that grew exponentially. I mentioned radioactive decay. Radioactive decay is basically a characteristic of non-stable elements. Excuse me. Some elements themselves are not stable. They have no stable state. Some elements are stable, but they have unstable isotopes, like carbon. Carbon-12 is stable, carbon-14 is not. When you have an element in any state that's unstable, it loses its mass over a period of time. And we measure, as human beings, I think it's worldwide, we measure how much they lose, how much of their mass that they lose, we measure it over what's called a half-life. So we measure the time, I should say, the amount of time it takes for that substance to lose half of its mass. Okay, half of its mass, half of its mass. Carbon-14 is like 5,700 years. So every 5,700 years, carbon-14 loses half of its mass. It goes from 20 to 10 to 5 to 2.5 to 1.25, so on and so forth. Okay. Let's look at example 8. Ra-225. That's the way to say radium-225. 225 is a radioactive isotope of radium-226. Okay. The radium-225 has a half-life of approximately 15 days. So every 15 days, radium-225 loses half of its mass. If we start with a 6-gram sample, so we're measuring mass now in grams, not pounds. We have a 6-gram sample of radium-225. How much of the original sample is left after 12 weeks? Okay, well, the way we do this is we write a model first, and then we'll deal with the 12. So we write a model first, and then we deal with the 12. So just like we did in the warm-up, let's write the amount t, the amount at any given time t, and instead of starting with 1, we're actually given an amount, which is what? The original amount? 6 grams. So that's our A value. That's our A sub O. And then since we measure it in half-life, and it tells us the half-life is approximately 15 days, what would be an appropriate base? 1/2. Yeah. And what is our x component going to be if it does that every 15 days? T divided by 15. Good. And I'm going to put a comma here to let people know that T is measured in days. Okay. If you want to change it to months or weeks or seconds or nanoseconds, that's up to you. The only reason we would ever want to change this if we said like every 3,000 days, right? We don't want to have numbers so big. So instead of measuring in 3,000 days, we might convert that to years or something like that so that we have a smaller number. But 15 is a reasonable number, so we'll just keep it as 15. All right, so now this is a formula. If I know the t, the time, I can plug it in and figure out the amount that's left. Or if I know what I want the amount to be, I can set it equal to, and I can solve for t. Which one am I given here? I want to know how much of the original sample is left after 12 weeks. Okay, So let's come over here and we say 12 weeks. If we're measuring in days, do I just want to figure out what A of 12 is?
No.
That's not what I want. Good. I need to know that 12 weeks is equal to how many days? Is equal to 84 days. Good. So I need to make my input match the units of my variable. So what I really want is A of 84. Now it's time to bust out a what? A calculator. So everyone can do this together. We can go to the Canvas, we can go to the standalone calculator, and we can go to the link that I gave you, and we can pull up Notability side by side, get down to our convenient 1/3 window, start the test, start the question, hit the A's up there, hide the toolbar, hit the 3 horizontal bars, get the calculator, and now we're square, right? That should be, if you do that often enough, it becomes second nature. It is to me. Or you can grab a yellow calculator. All right, so there's a couple ways to do this. I could just type it in directly into the home screen. 6 times 0.5 caret to the 84 divided by 15. I could do that. 0.5 is another way to say 1/2, so it's an easy way to do that. And I get 0.123. Hey, 0.123 grams. The other way to do it, if you want to actually see the curve, is to type it in. 6 times 0.5 caret to the x divided by 15th power. And now we set a window. I like graphing it because it requires you to think about a reasonable window. What would be a good x min? We're measuring time in days. 0. What would be a good x max? Well, if we're going out to 84 days on our calculation, maybe something that includes 84, like 100 would be nice. And you can leave your x scale to 1, or you can turn it off to 0, either one. Y min, we're measuring the amount, the mass. Can it be negative? No. So 0 is always a good lower bound. And then, of course, since it's decay, we know it started as 6. It's never going to be greater than 6, is it? So I'm just going to put 10. Now I hit graph, and we see it decay. Right? And now you could just hit trace, type in 84, hit enter, and you get the same amount. So that's another way to do it. Or you could go to the home screen, and now you can recall alpha trace number 1 of 84, and you can get the answer that way as well. So a couple ways to do it. This is when you're given the input. It's just a plug and chug problem. You just need to know the output. Plug it in. Okay. That's the first part of this question. The second part B, this is part A. Every day in here is part A, right? It's a part A, party in the USA. How many days will it take the original sample to decay to 1 gram? Well, we know it's going to be within 84 days, right? Because it's already way below a full gram. But in this case, how am I going to use the model? Do I want to plug in a 1 for t or set it equal to 1? I set it equal to 1 this time. So I'm going to get 6 times 1/2 t divided by 15, and it's going to equal 1. Now, once again, when we learn about properties of logs, we're going to be able to solve this algebraically. But we don't know about logs just yet, or we're not going to review them from Algebra 2. But in order to unexponentiate this and get the t onto the ground floor so we can solve for t algebraically, we need a log. We need to know about the inverses of exponents, which are logs, and we don't know that yet. So we're going to solve this one graphically. So if you hadn't graphed it yet in Y1, now would be the time to graph it in Y1. So I have it in Y1. And what are we going to graph in Y2? 1. And I already picked my window. So if I hadn't picked my window, I'd have to sort through my window. Hit graph, and now you're going to see it intersect. And of course, now it's easy. Second trace, number what? 5. And then it's just enter, enter, enter. Come on in. And then we put t equals, don't forget to put t equals 38.774, and then we put our units of days. So on our final numeric answer, we always put units. And we always round or truncate to 3 decimals. It doesn't matter. There you go. A real life example, ripped from the periodic table. Radium 225. I think 225 is the what? Is that the atomic mass of radium? I think that's what that number means, right? Any chemists in here? Chemistry?
Yeah,
Yeah, like if you say carbon 12, 12 is the periodic table number, which is its mass, I believe, or it's not the mass. No, it's atomic number. Yeah, which represents the what? The number of electrons it has?
No, I'm pretty sure the number is the atomic.
Neutrons, maybe.
It's the mass, because you could have different numbers.
It is the mass?
Yes.
Okay.
Yeah, neutrons.
There you go. Okay, neutrons plus protons.
Yeah, the mass of radium is 226.
Okay, very good. Okay, yeah, yeah. So it is the mass. That's what I thought. The atomic number is the mass, and it's neutrons plus protons. And the electrons can vary so wildly. It's just like, yeah. But that's why radium 226 is unstable. It's got an extra proton in there, and it's like I need to get back to homostasis. Is that a word? Homostasis, equilibrium. Let's use that. All right. Questions on example 8. Stay away from radium 226, guys. It's radioactive. Or wear a lead vest cautiously when you approach it. Suppose a radioactive sample loses 43% of its mass every 9,876 years. What percentage of its mass will be left after 2,000 years? Oh, so now we're working with percentages. So kind of like in the warm-up here, I am not given an initial amount. And when you're dealing with percentages, you actually don't need an initial amount. Suppose a radioactive sample loses 43% of its mass every 9,000 years. All right, step 1, based upon that, we should be able to write a model. So let's write the model. A of t, the amount at any given time t. If you're not given an initial amount, what can we use? 1. We'll use 1. And then here, Brady, since I'm giving a percentage, it loses 43% of its mass. Is this going to be decay or growth? Decay. And what's the base? Is it 0.43? It's 0.57. There you go. Now we have to find the difference of 43 and 100 because the model itself doesn't tell us how much we're losing. The model tells us how much we have, which is how much we have retained, which is the difference from 100. And then what would the exponent be? T what? Divide by 9876. Yeah, and then we'll make a little note here that T is in years. T is in years. Okay. Now that we have that, it says what percentage of the mass will be left after 2,000 years? Yeah, we plug in a t equals 2,000. So we show that in function notation by doing a of 2,000, and then we could just plug it in. Now I'm going to do it the other way again. I like to plug in the model into y1 in case I have to use it again for anything. I have it right there, and I don't have to plug it in again. So I'm going to type in 0.57 caret x divided by 9876. All right, now I don't need to graph it just yet, so I'm going to go to my home screen now, flush, and hit alpha trace number 1 of 2000. And I get 0.892. 404 8855. Is that my answer? It's not quite. That just tells me that if I started with 1 gram, I am now left with 0.892 grams. Yes? I need to figure what percentage of 1 is 0.892. What percentage of 1, my original amount, is 0.892? 89%. Very good. The beauty of starting with 1, or you can even start with 100 if you prefer, and then you don't have to worry about converting at the end. You can just convert 0.892 to a percentage by moving the decimal 2 places to the right. So 89.240. Now I have to report 3 decimals on my converted answer. So that's going to involve the 0. I can't just drop the 0. It's not a terminating 0. It's just part of the accuracy here. 89.240% is left. Or instead of is left, let's just use one word. Remains. Is that a reasonable number? Yeah, we haven't even been through one half-life yet, right? We've been through maybe a fifth of a half-life, something like that. All right, now the next question. After how many years will the sample contain 22% of its mass? All right, so now, since I'm given the percentage and not the time, I need to set A of t equal to something. What do I set A of t equal to? 0.22, which is 22% as a decimal. Now I can set A of t equal to 0.22 like that, or I could say 0.57 to the t divided by 9876 equals 0.22. They both mean the same thing. They both tell me what you're doing. This is the way that you would write it if you were using your calculator, just because it's more compact, it's more concise. This is the way that you would do it if you were doing it algebraically, which we'll do in the next section. Because algebraically, you actually need the other expression on the other side so that you can manipulate the variables and the numbers to solve for t. Okay, but either way, this would get a check on a quiz by showing me that you're setting an equal to 0.22. And then since I already have it in y1, I'll just go down here to y2 and I'll put 0.22. Now, if you hit zoom 6, you're not going to see much, right? It looks like two horizontal lines. I need to think about a window, don't I? And what did I say? We need to what about a window? Think about a window. That's the whole purpose of this class. All right. So let's start at 0. What would be good to go out to? What would our time value be? 30,000. That's not bad. That's like 3 point something half-lives, isn't it? A half-life is almost 10,000. So 30,000 is reasonable. Let's just leave that as a 1. Our y min could be 0. And what would be our y max? 10 is fine, but remember, we started with 1, didn't we? So if we go up to 10, we're going to see a lot of space above 1. It's decay. We know it's not going to be bigger than 1. 2. Let's go to 2. Okay? Now you hit graph. Hey, 30,000 was not a bad guess. If you didn't see them intersecting, you would just change your x max to something bigger, right? Until you did. In fact, I think I'm going to go out a little further here. I'm going to change that to 50,000. I not only want to see them intersect, I want to see white space on either side of the intersection between them. So I know for sure. Okay, there it is. Now I go second trace number 5. Enter, enter, enter. Come on in. And then don't forget, we get t equals 26602.068. And are there units on that? Years. Good. So on the quiz, I would give you a check for setting it equal to 0.22 in either one of those fashions. I would actually give you a check for saying t equals. That's important. I would give you a check for the answer to 3 decimal, and I'd give you a check for the years. All of those components are critical to communicating what you're doing mathematically. It's not just about getting the right answer, is it? It's about communicating how you got it. Notation, notation, notation. No notation? No points. Okay. Comments or questions? All right. Sadly, let's move on to something that is very, very real. Over the years, there have been several nuclear reactor meltdowns that have taken place. The most recent one that I can remember was still several years ago in Fukushima, Japan. It was a big deal. There was also 3 Mile Island, but the most famous of them, perhaps, was Chernobyl. Have y'all heard of Chernobyl? They actually made a HBO series about it, Chernobyl. It was called Chernobyl. Yeah, it was pretty good. It was all about Chernobyl. Chernobyl, Ukraine, is where it's at, is located. So it might be Chernobyl, Russia, unfortunately, unless the U.S. can intervene and stop it, which, that's political. We don't want to talk about that. Are we obligated to? We could just send money. Anyway, let's read this. The number 4 reactor at the nuclear power plant at Chernobyl on April 26, 1986. I remember when this happened. The 80s were rough. We had Chernobyl. We also, around the same time, we had the Challenger disaster where the space shuttle blew up, killed 7 astronauts, including Krista McAuliffe, the first teacher in space. Most of these were short-lived. I'm sorry. When it exploded, when it melted down and exploded, it released over 100 radioactive elements into the atmosphere. 100 radioactive elements. Those in general are not good to be exposed to. They cause mutations in the human body. Okay? So there are still so many radioactive elements that are there. It is still unsafe to live there. And you might have heard in the news or seen pictures of, they are currently in the process of building a giant dome over the nuclear reactor to contain the spread of these elements that are still there because their half-lives are so long. Iodine, strontium, and cesium were the most dangerous of the elements released, and they have half-lives of 8 days, 29 years, and 30 years respectively. The isotopes, strontium-90, cesium-137, are therefore still present in the area to this day. While iodine is linked to thyroid cancer, see that, strontium can lead to leukemia. Cesium is the element that traveled the farthest and lasts the longest. This element affects the entire body, especially can harm the liver and the spleen. Oh, there it is. Fukushima, Japan was 2011. Okay. It rivaled Chernobyl's levels. It was a big one, too. That was a bad one. So anyway, it's like a ghost city, a ghost town in Chernobyl, Ukraine. It's highly guarded. You can't get in there unless you have special approval or you're really sneaky. And when you go in there, usually you wear protective gear or you don't stay in too long. Let's look at this. Part A. If 2,000 grams of cesium-137 were released at Chernobyl, how many grams of cesium-137 are present there today? All right, so it's kind of the same idea we did in the previous one, but like again, it's something we can all relate to. We've heard of Chernobyl. So A of T, the amount of cesium at any given time in years, is going to be the initial amount, which says 2,000, so 2,000 grams. And what would be the base? We measure these in half-lives. And what would be the exponent if it says up here the half-life of cesium, which is the third one listed, is 30 years respectively? It would be T over 30. Okay, so there's the model. We'll say that T is in years. And this is for cesium 137. All right, part A, 2,000 grams were released. How many are there today? So in part A, 2023 corresponds to what T value if this happened in 1986? 37 years ago, right? So it's barely been a single half-life, hasn't it? So it should be less than 1,000. It went from 2,000 to 1,000 in 30 years. It's been 7 additional years. So we'll just let T equal 37. How do we communicate in a function notation that we're plugging in a 37 for T? What do we write? A of 37. Good. So now we're back to kind of like notation. You would certainly get a check for the model if this were a quiz, but now we're going to put A of 37. That's going to be a check. And now we can either plug it in or, like I like to do, let's go ahead and type the equation in Y1 and see what the graph looks like here. 2,000 times 1/2, which is 0.5. It's easier to use 0.5 raised to the x divided by 30th power. Let's go to the window. We'll go from 0 to, we don't need to go to 50,000 now, do we? No. Let's give it what? 2,000? Okay. That's still quite a bit, right? But we'll go to 2,000. Y min is 0. What should Y max be? If we started with 2,000, it should be something bigger than 2,000, like 3,000. If we go 10 half-lives, that's 300 years, right? If we go 10 half-lives, that's 300 years. Let's actually trim that down instead of 2,003. Let's go to 300. That'll give it 10 half-lives. There you go. Now I have it in Y1. I can see it decaying. Now I'm going to go to the home screen. I don't really want to do it from the graphing screen. I want to get you on the habit of going to the home screen. and now we'll hit alpha trace number 1 of 37, and boom, you get 850.667. And what are the units? Grams. So if this were a quiz tomorrow, you get a check for writing the equation, you get a check for the A of 37 notation, you get a check for the answer, and you get a check for the units of grams. So that's still quite a bit from the original. It's still there, right? Which is why they're still building the dome over it to try and contain the continual spread of this thing. If 20 grams is considered a safe level, 20 grams is considered a safe level. How many years is it going to take for cesium-137 to reach this level? Well, what do we have to show now? A of t equals 20. That's a check. Now we go back to our graph. Instead of solving it algebraically, we'll type in a 20 and we hit graph. And ooh, that's not, it's way down the line, isn't it? Let's see if it actually intersects here. I can't really see the white space above and below, but I think it might cross. Second trace number 5. We'll let the calculator check. Enter, enter, enter. There it is. T equals, that's going to get a check. 199.315. Check. Years. Check. 200 years. Who's going to be around in 200 years? That's alive today. No one. Especially someone who's getting exposed to cesium-137. Right? There you go. So these, it's not like you could just go in there like with the shop vac and just shop vac all the cesium-137 and take it away and bury it somewhere in the ocean or under a pile of wood. This stuff permeates everything. It's radioactivity. It just permeates everything. It's like Bluetooth, right? You know how Bluetooth just exists in the ether? Bless you. This is like Bluetooth, okay? Now let's do something here. Let's check. Let's go. Yeah, we'll go to Google, so we don't have to take a field trip to the library. We'll just type in dome. It might be finished over Israel. Dome over Earth Bible. What? Yeah, that showed up in my search. I want dome over Chernobyl. New safe confinement. There it is. Here's a picture of what's going on. 2016, the inaugural Arch operation. Yeah. So blah blah blah. Yeah. So 2016. But it's built. So now it's containing. It looks like there's another containment under the arch that's capping the reactor there. So that they've got double wall insulation. But it's not just like supposed to be waterproof. That stuff is like it's designed to be where the radiation can't permeate or infiltrate. And look at this. I like it. That second layer that we see underneath there, that's the emergency sarcophagus. That's a great word, right? That's what they buried the mummies in. The emergency sarcophagus. That was built in 1986. The emergency sarcophagus was built in 1986. So they tried. They tried right away to cap it. Oh crap, this stuff's getting out. This is bad. Let's cap it. But it cracked and it was insufficient, so now they just built a dome over it. Now people still are, that doesn't mean that people can still come back in and inhabit Chernobyl. I did watch an episode of Ghost Adventures years ago. These are guys that go and they investigate paranormal activity, and they got special clearance to go into the Chernobyl area, and they were investigating a school. And I kid you not, this was probably like in mid-2010s, so maybe 2015 or so. And to this day, right, that was still 30 years later, they were in the school, and there was abandoned desks with paper and pencils and textbooks still sitting on the desks. So imagine right now that we just had this air siren go off and they evacuate now, leave everything behind, evacuate now. And we ran out and we grabbed only just our wallets and our precious cell phones, right? and we let everything else would be left in here, and we would never come back in and retrieve it. That's what it felt like. It was an eerie feeling to see all that stuff just still sitting there. You can imagine the urgency with which those students evacuated, terrified that they were going to get radiation poisoning and start growing a third arm out of the middle of their stomach, which could be handy if you're trying to do more homework, right? If you teach it to write. Anyway, Chernobyl. There it is, Chernobyl. Questions so far? All right, let's jump down to example 11. We talked in the previous section about logistic growth. Logistic growth, remember, looks like this. Here's the characteristic for logistic growth. You have this exponential function that has a horizontal asymptote at 0, and it grows exponentially at first. Okay, so this is exponential growth right here. But then it gets to this point where it starts to grow the other way, and then it levels off to some upper horizontal asymptote called y equals L. And L is your carrying capacity, or your limit to growth. So exactly halfway between the upper horizontal asymptote and the lower one, which is at 0, so this is at y equals L halves, that's where we have this right here, which we call the what point? That's the inflection point, yeah. That's a very important point. That's where the curvature changes. That's where it goes from concave up like a cup or part of a smile to concave down like a frown. That's also where this is growing at the fastest rate. That's another important aspect of the inflection point, where the curve is growing at the fastest rate. So not everything that begins to grow exponentially can continue to do so indefinitely, because there are limitations. Whatever those limitations are, that's y equals L. All right. Here's what the equation template looks like for a logistic equation. That's what the template equation looks like for a logistic equation. It's f of x equals L. This is your limit to growth. It sits proudly in the numerator. And then it's all over 1 plus c e to the negative kt. So if you take inventory, I have 1, 2, I have 3 unknowns. I'm going to close this window here. I have 3 unknowns. If I ask you to write an equation of a logistic model, it's not as simple as what we did right here, where we just had 2 unknowns, the base and then the a sub o, right? We have to have 3 pieces of information. With 3 unknowns, we need 3 pieces of info. Well, let's try it out here. We're going to try and write the equation. This will be the last thing we do today, probably. F of 0 equals 20. Right, if this were exponential, 20 would be my y-intercept, yes? But believe it or not, for logistic, this is not necessarily the y-intercept. It's not necessarily the y-intercept. Or actually, it is the y-intercept, sorry. It's not necessarily, I'm getting my ideas confused. It's not necessarily the c value, okay? It's not necessarily the c value. If I were just to look at y equals c e to the kt, c would be the y-intercept. Okay, c would be the y-intercept. But because it's in the denominator with a 1 plus c, we can't just say, in other words, we can't just say c equals 20. It is the y-intercept. For sure it is the y-intercept. I didn't mean to say that it wasn't the y-intercept. It gives us certainly a point that we can use to plug in, right? It's a point, an xy, that satisfies the equation. Here's another ordered pair that satisfies the equation. 3 comma 1 tranny. 3 comma 1 tranny equation. I got 2 points. I need a third piece of info, don't I? The limit as x goes to infinity equals 500. What the heck does that tell us? As x gets bigger and bigger and bigger, the y values are approaching 500? What is 500? That's your limit to growth, isn't it? That's your carrying capacity. That's your L. So we know L right out of the box. We do know L right out of the box. We don't know the other. So we're going to play this in pieces here. So if I know that L equals 500, I can get the model this far. I can say f of x is equal to 500 times 1 plus c times e to the negative kx power. So now I've used one piece of information, that's the end behavior limit, and I've got my 500 in the numerator. But now I still have two unknowns. Well, I still have 2 points that I can use. Which point would you like to plug in first? Which one might be easier to work with first? 0, 20, okay? So I'm going to do that. I'm going to say at 0, 20, colon. This tells me you're plugging in a 0, 20, just like above I said L equals 500. We're going to get 20 equals 500 all over 1 plus c e to the, what is 0 times negative k? 0, right? We get e to the 0. So now if I work through this, I get 20 equals 500 all over 1 plus c. E to the 0 is 1, isn't it? Okay. Now I got to solve for c. Now here's an algebraic trick, and I think you can visualize this. The 20 and the 1 plus c in this proportion, they can switch places, can't they? It's like multiplying both sides by 1 plus c and dividing both sides by 20. Those two right there, the top left position and the bottom right position, these can switch places. If you want to do that in 2 steps algebraically, or you could put the 20 over 1 and you could cross multiply if you want to do that. That just takes more steps algebraically. I'm going to write this as 1 plus c equals 500 over 20. Now it's going to make it easier to solve for c. What is 500 divided by 20? 25. And so if I subtract 1, I get c equals what? 24. So remember I told you that it is the y-intercept, but it's not necessarily the value of c. C, in fact, is 24. So where does that leave us now? If I plug c into this model, I get f of x equals 500 all over 1 plus 24 e to the negative kx. So I'm doing it piece by piece. Now I plugged in my 500. Now I've plugged in my 24. I still have to find k, don't I? So I need one more piece of information. Do I have one more piece of information? I do. So we're going to say at the point 3 comma 120 colon. I get 120 equals 500 all over 1 plus 24 e to the negative 3k. I'm plugging in a 3 for x. X is 3. So it's negative k times 3, which is negative 3k. Yeah. All right, now I'm going to do the same switcheroony here. I'm going to switch those around, and I get 120, 1 plus 24, e to the negative 3k equals 500 over 120. So 1 plus 24, e to the negative 3k would have to equal what? What's 50 divided by 12? Does it go in evenly? Unevenly, right? 25/6. Okay, now from here, it's going to get kind of gross if we continue algebraically. We are going to need logs. So we have an option here. We can either graph this in y1 and this in y2 and find the point of intersection and get k as a decimal, or we can learn logs and continue to solve it algebraically and find the exact value of k. All right? We don't have time to learn the logs today in order to do that. That's what the next section is. And believe it or not, the calculator, although we know how to do that, we don't have time to do that today. So we'll save that for tomorrow. So tomorrow we'll quiz. I will not ask you to quiz like number 11. Okay, like the one we're doing. Number 11 is not on the quiz. But anything that we've covered before example 11 will be on the quiz. And then after the quiz, we'll finish the notes. And it looks like the homework will be due Friday morning at 9 a.m. Okay? Any questions on today? What a fantastic day it was. We got to get exposed to radiation, but not exposed to radiation.